So now that we have a little bit of kind of a high level understanding of SN1 and SN2 reactions, let's talk about how a variety of different components, like our leaving group, for example, can impact our reaction. So our leaving group is going to be very important in both our SN1 and our SN2 reactions. That leaving group leaving is a part of both of our rate determining steps. In SN1, it is literally how quickly does it fall off, and in SN2, the concerted reaction, you have both the attack and leaving group leaving at the exact same time. So your leaving group is super important, and the stability of it is going to matter a lot. Now, traditionally, some of the best leaving groups are going to be things that are good at accommodating a negative charge. However, you don't want them to be too basic. You're kind of looking for a nice sweet spot where you have a kind of weak base. So halogens make really great examples of leaving groups. Now, if we think of our halogens, our fluorine, our chlorine, our bromine, and our iodide, the bigger the group is, the better of a leaving group it's going to be. It's able to accommodate that negative charge more favorably. It's also a little bit further away from its nucleus based on its size. So your iodide is actually going to be a really, really good leaving group, where your fluorine is actually going to be kind of a more sucky leaving group. So for example, if you were comparing two different structures, one which had a chlorine and one which had a bromine, and you were asked to compare the rate of the reaction for those two, your bromine substrate is probably going to have a faster reaction because bromine is going to be a better leaving group than chlorine. Now, there is a handful of species that are really not going to be good leaving groups, and you're not going to see them work very often. Just a carbon or hydrogen stuff, nitrogens, ethers, or alcohols. And one of the most commonly available functional group on a bunch of structures is going to be an alcohol. And I'm going to say this a million times, kind of like the pKa of a carboxylic acid is 5, just to try to get it to stick in your head. Alcohols are not good leaving groups. And we'll even go ahead and write that fully out. Alcohols are not good leaving groups. It does not matter how many times I say this, students still love to make alcohols leaving groups. This entire video is going to focus on how we can convert alcohols into something that is a good leaving group, because alcohols are not good leaving groups. You cannot have an alcohol and then just magically say it falls off. That doesn't happen. So if you have a structure that has an alcohol, there is going to be one of two main ways in which we can change that alcohol into something that can be a good leaving group. One of them is going to be an acidic condition. One of them is going to be a basic condition. You kind of choose the one based on a variety of other factors, like how does your substrate do, things about like your nucleophile, things of that sort. So the very first one in which we can convert alcohol, which is not a good leaving group, into something that could be a good leaving group is by using an acid to convert an alcohol into a oxonium. Now, this is actually going to be something that's going to be kind of familiar with you because in general chemistry, and even in acid base, we talked about the idea of hydronium, which is going to be kind of like water with an extra hydrogen. That extra protonated alcohol is an oxonium, which is kind of like a sister to hydronium. So let's go ahead and consider here, we have a substrate. This is tert-butanol. I have 1, 2, 3, 4 carbons, and they're tertiary. So that's T-but, and then the ol for the alcohol. So tert-butanol is going to react here with our acid, and our acid right here is HCl. And you can use all kinds of different acids. And if you expose a hydroxyl group to an acid, you get a very traditional acid-base chemistry. So your alcohol is going to be a very good base. It has some lone pairs, and you now have an acid because you've added an acid. What you can do is you can get acid-base chemistry where your alcohol attacks and steals a proton from your acid, and then the chlorine, which is going to be your conjugate base, forms. That right there is then going to give you what is known as a oxonium. So an oxonium, and we'll go and actually write that out for you. Oxonium is going to be an oxygen that has a positive charge and is connected to some carbon stuff. Now, if you have a hydronium, that is going to be when you have all hydrogen stuff. You don't have any carbon stuff. Once you have the carbon stuff, we call it an oxonium. But it's the same idea as a hydronium. And your Cl minus. Now, at this point, your oxonium is a good leaving group. Alcohols are bad leaving groups. Oxonium, which is just like water, is actually a really good leaving group. If we wanted to think about this being a leaving group, if this leaves, what would happen, as we kind of showed down here, you would then get your tertiary carbocation, and then you would form water. And water is going to be a lot more stable and a lot weaker of a base than your hydroxide. So it's going to hit our rules that we were thinking about earlier. So alcohols are not good leaving groups, but if you react with an acid, you can form an oxonium, and an oxonium is a good leaving group. So that's our kind of first condition or first idea of if you do have an alcohol and you need to do SN1 or SN2 chemistry on it, you can change it into a better functional group, such as an oxonium, in order to make it leave. The second one is doing a reaction where you can make yours, instead of having an OH, you can make it into an OR that's going to be less basic. And there's going to be two really common ways that we can do this. We can convert an alcohol into either a mesyl, that's the MESYL, which we will abbreviate as MS, or a tosyl, TOSYL, which we'll abbreviate as TS. Capital first letter, lowercase the second. So your mesyl, which is this, or your tosyl, which is this, are common ways to decrease your basicity of an alcohol. So you'll see that each of these has a chlorine, a mesyl chloride or a tosyl chloride. You can take those and react those in the presence of a base with your alcohol. And what that will do is that will turn it from an alcohol to a mesyl or a tosyl group. And those are going to be good leaving groups. Now, these are going to happen through a mechanism that's kind of like SN2, to be honest. You have your oxygen, which has a lone pair. It's going to come and attack this sulfur. There's some extra stuff that we're going to learn in Orgo 2. And your chlorine is going to leave. This is a little bit oversimplified, but the right general process. In the presence of a base, the base is actually going to go through and actually remove this hydrogen. And then that would then give you your O and then your bond to, for example, your mesyl or your tosyl. Often you'll write Me or CH3 for the far end of your mesyl. This sulfone, so sulfur with two double bond oxygens, either with just a methyl or if you have a toluene-like structure where you have a benzene ring then a methyl, are going to be common examples of things that you can do to substitute. So if you wanted to show like another example, like from like the one above, if you have T-butanol, you can take this and then react this with, maybe even just show it just all on the arrow. You can react this with base, and then you can write out just literally TSCl, and then that would then give you your O and then TS. And this OTS, which is your tosyl, or another example of that would be your mesyl, which would be OMS. Those are examples of good leaving groups. So kind of summary of a lot of the thought that we were thinking about with leaving groups. Halogens are good leaving groups, and the bigger the halogen, the better the leaving group. So iodide's a great leaving group, bromine's decent, chlorine's okay, fluorine kind of sucks. Alcohols are not good leaving groups. If there's one thing you got out of this video, I really hope it's alcohols are not good leaving groups. There are two ways in which you can convert an alcohol into something that can be a good leaving group. Those things are either using acid to make an oxonium, oxoniums are good leaving groups, or with a methyl or a tosyl, because they are also good leaving groups. And those are going to be some strategies where if you do have an alcohol, you can turn it into something better. That's going to go ahead and wrap up our discussion of some leaving groups that we see in common SN1 and SN2 reactions.